Okay, matter part 2, kinetic theory, phases, conservation of mass, physical and chemical properties and changes of matter, pages 51 through 88. Please correct your text answers as you go through this video and fill in the compare and contrast outline for your notes. Comparing physical and chemical properties and changes. Physical properties are defined as a characteristic or change of a substance that can be observed or measured without a change in chemical makeup. Here are some examples. Melts easily, shiny and silver, it's rectangular in shape, it's a solid, liquid, or a gas, it has density, and then another one that we can add is boiling point. Melting point, that would be this one here, melting point. So those are examples of physical properties when we want to describe some kind of matter. So why is it helpful to know physical properties of objects, aka matter? Physical properties remain constant. Thus, you can use your observations or measurements of these properties to identify substances and then determine its uses. Define density and give the equation with the units of measure. So how dense a material is the measurement of how much matter is contained in a certain volume of a substance. Density, D, equals M for mass divided by V for volume. Density and hot air ballooning. Let's watch a little film on that.
How in the world does a hot air balloon work? Man has been sailing along in hot air balloons since 1783. Over the years, these colorful objects have been used as military tools, advertisements, and just a great way to spend the morning. And in 200 years of ballooning, very little has changed. Why talk about it? Let's take a ride. For a topic this hot, the airship Curiosity is wasting no time heading for the hills. Located along the Rivanna River, Charlottesville, Virginia is nestled in the southwest mountains and just east of the Blue Ridge and the Shenandoah Valley. Charlottesville is home to the University of Virginia, Monticello, the home of Thomas Jefferson, and quite a few hot air balloon enthusiasts. Crisp autumn mornings find the balloonist up with the sun, putting together the pieces for morning flying.
Well, you have to stitch your basket assembled, lay it down, attach the balloon, then we use an inflation fan to cold pack or cold inflate the balloon.
Mandy Rafano has been a licensed hot air balloon pilot for 10 years. Once she and her crew get the basket in place and the balloon inflated, it's time to heat the air inside using propane burners. How hot? How about 212 degrees or so? That's the temperature the water begins to boil. The burners continue to fill the balloon with heat until the ambient air is hot enough to lift it off the ground. Used as an adjective, the word ambient means surround, encircling. In the balloon's case, the surrounding air is heated up to cause lift. Hot air balloons slowly fill and rise majestically in the early morning light. Colorful for sure, but did you know that there's basic science at work here? Yep, the ideal gas law, and our old friend Archimedes and his famous principle. For example, the ideal gas law is a mathematical relationship between the volume pressure and temperature of a gas. For a given quantity of gas, the pressure V multiplied by the volume V divided by the temperature T remains a constant. Huh? That means when a gas like air is heated in a balloon, its volume will increase. So the volume increases and fills the balloon. Soon it's full and flows out the hole at the bottom. Hot air contains fewer molecules and will be less dense than cooler air. Remember our old friend Archimedes? When we learned about how a boat floats, Archimedes told us that when an object is suspended in a fluid, the buoyant force acting on an object is equal to the weight of the fluid displaced. So if an object is less dense than the fluid, it floats. Although hot air balloons can come in many shapes and sizes, they all have three essential parts: the burner, which heats the air, the balloon envelope, which holds the air, and the basket, which carries the passengers.
That horizon up there has a bit of substance.
So, what's missing from this picture? How about a steering wheel or a rudder?
We actually can steer the balloons depending on the varying winds of the day. If the winds allow us, we can almost steer them like an airplane just by finding different layers to ride out.
Skilled pilots can read the air, so to speak, and maneuver the balloon horizontally by changing the vertical direction. To move in a particular direction, a pilot ascends and descends to the appropriate level and rides with the wind. Since wind speed generally increases as you get higher in the atmosphere, pilots can also control horizontal speed by changing altitude.
You may find due south at 1,000 feet and east down on the surface, maybe west up high.
A pilot heats the air with the burners to make the balloon rise. To descend, there are two methods.
Either let the balloon start to cool off, it'll initiate a slower descent, or this particular balloon that you flew in had one large deflation vent called the parachute valve. We'll give a good pull on the red line for about 3 seconds, and that'll vent a large amount of air out and initiate a much faster descent.
And eventually that descent leads to a landing, where a balloon chaser helps bring it to the ground. After all,
Ballooning definitely has its ups and downs.
And did you know that in order to pilot a hot air balloon, a person must apply for a pilot certificate from the Federal Aviation Administration? See? You gotta know your stuff.
All right. So take a moment to jot down some information on hot air ballooning for question number 6. All right. Moving on. So we said physical properties: melts easily, shiny, silver, yeah. So basically, in essence, we are identifying an element or molecule's outer appearance. Okay, that's a physical property. Now we're going to get into chemical properties. Definition: the way a substance reacts with other substances to form new ones with different properties. So some examples are rust. Rust is when oxygen in the atmosphere bonds with iron. Fe stands for iron, the Latin name iron, ferrum. And when those two bond together, you don't have anything shiny and silvery and metal anymore. You now have something that is brownish red and crumbly. It no longer is iron or oxygen by itself. When it bonds together, it forms a new compound. Flammability. Oxygen is everywhere, and oxygen is the main ingredient in lots of different chemical properties and chemical reactions on our planet. Tarnish, here we are again, oxygen. Oxygen bonds with silver. Ag is silver, and so then it gets kind of that dull look to it. How an element or a molecule will bond with others is what a chemical property is all about. Okay, classify the following as either a chemical or a physical property. Shiny and silvery would be a physical property. It melts easily. This is its melting point. That's a physical property. Burns in air. So as soon as you have burning involved, you no longer have the same thing. If you burn a log of wood, after Oxygen has interacted with the wood, you end up with something that doesn't look anything like wood anymore. It is no longer wood. It is now a pile of ashes and a bunch of gases and carbon that have been released into the atmosphere. That is a chemical change. Boiling point is physical. All you're doing is giving enough energy to the atoms and molecules so that they start to move faster and escape from a liquid phase and go into a gas phase. Has a density. Density is a physical property. We're describing how much matter is in an object, makes up a specific volume of an object. Tarnish, remember, that's with the oxygen. So whenever you have moist air, water in the atmosphere, oxygen, they combine on the silver and turn it into something we call tarnish. So it's bonded to the silver. It's no longer silver. It's what we would call it tarnish. So that's a chemical reaction. It is yellow and rectangular, physical property. Good conductor of electricity is also a physical property because we're talking about how easily does it give up its electrons. You haven't changed the molecule or the element into anything different. You've simply moved some of its electrons around. It's the protons, remember, that defines an element. Okay, now we're on to physical and chemical changes. Physical and chemical changes. Definition of a physical change: a change in physical form or properties of a substance without changing its composition. So here are some examples. Quartz into sand. Wave action on the oceans, shores, or large lake shores pounds the rock structure into smaller and smaller and smaller bits, creating sand. Peanuts into peanut butter. It's still peanuts. It's just that now you have changed its shape. You've turned it into a more liquidy shape instead of its solid peanut form. Okay. Chopped wood. You start with a piece of wood, you chop it down, 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 you still have wood. You haven't turned it into anything different, you've only made it smaller. Tearing a piece of paper, again, the little pieces are still paper. You haven't changed that fiber we call paper into anything different. Definition of a chemical change: when a substance changes its composition by forming one or more new substances, therefore we have a change in its chemical makeup. We've changed the molecule or the atoms that are involved in some way. Here are some examples. When we inhale oxygen gas, we exhale carbon dioxide. We have now had a chemical change. The oxygen has bonded with carbon, which is a waste material that we need to get out of our body from metabolism. Eating and digesting food. Let's say you have a bowl of cereal this morning. You eat that, and then it goes down through your intestinal tract, and starting with your saliva, it's broken down into different things. And when it comes out the other end, I guarantee you it's not going to look or smell or taste like Cheerios. Okay, it's something completely different. That is a chemical change. Rust we've talked about. Okay, so when iron bonds with oxygen, we have created a different molecule. No longer does it look or act like iron. No longer does it look or act like the gas oxygen. It is now a molecule called rust. Fruits ripen, changed by digestion from bacteria that are sitting on that fruit. So, is dissolving considered a chemical or physical change, and why? It is a physical change because all we're doing here is dissolving, or it adds just enough energy. When you stir sugar, for instance, in water, you're adding just enough energy to break down the sugar crystals into smaller pieces of individual molecules. These molecules then spread out between the water molecules. So the molecules of sugar spread out between the water molecules. The sugar molecules do not break apart or change. The individual elements remain the same. And when we take a sip of that sugar water, we can taste the sugar. We can taste the physical properties of water. So we know that both of those are in there. Nothing has been changed chemically. 16. If water is lost when clothes dry, is this a chemical or a physical change? Well, this is also a physical change. Why? Because just enough heat is added to the clothes to evaporate the water. This means the water changes phase from a liquid to a gas. The clothes are still the same. They have not changed into anything different. The blue jeans are still blue jeans. They're just no longer wet with that water that was in between the fibers. So this is a physical change because now they are lighter in color and not wet.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
Whoa, that was crazy. All right, take a moment to jot down your your description of what just went on there on your outline for your notes. Okay, describe what happened to the gummy bear, and is this a physical or a chemical change, and what were some of the observations that led you to that determination of physical or chemical change. Okay. Next, the kinetic theory of matter explains the forces between molecules and the energy that they possess. This theory has three basic assumptions. We've already learned about kinetic energy. That is energy expressed as motion. So molecules and atoms, these all have kinetic motion at the cellular and molecular levels. Okay, so one basic assumption is volume, due to the space between molecules in matter. So volume is going to be determined by how much space is between molecules in any kind of matter. Second basic assumption is the molecules and atoms are in constant motion. This motion is different for each of the states or phases of matter. So if it's a solid object, there's less molecular motion. There's less space between the molecules of matter. The more energy, the more these atoms and molecules move away from each other, therefore increasing the space between them, and you have a greater volume due to that motion. When molecules collide with each other or with the walls of a container, we assume there is no loss of energy. And the reason is because they are so incredibly tiny that whatever minutia of amount of energy they lose when they slam into something is really not anything that chemists are concerned about measuring. So we assume that they're moving at the same speed all the time, no matter what they hit. Now, there are actually 4 states of matter, not just 3. We have solids, liquids, gases, and something called plasma. I want you to watch this short video on what plasma is.
Hi, my name is Michael Slant. I'm a junior at the University of Maryland, College Park. This is Buddy Cruz. He's a grad student here as well. And we're here to tell you about plasma, the 4th state of matter. And we're here researching plasma to find out how plasma can be made to create some pretty amazing phenomena. So hope you enjoy this video. Thank you. Plasma. It is the basis of some of the most spectacular phenomena in nature. The violent spark of lightning, the luminescent northern lights, even the burning brightness in the core of every star in the universe all have their origin in plasma. Man-made plasmas include fluorescent light bulbs, neon signs, and plasma televisions. When we think of plasma, we often think of its intense otherworldly glow, which almost seems supernatural. However, plasmas contain underlying physical concepts. So what is a plasma? Let's first look at a gas. A gas has a positive core with the negative electrons orbiting around the core. A plasma is a gas that is heated to the point that the individual gas atoms break apart into a collection of positively and negatively charged particles. The distinct glow of a plasma is created by the occasional recombination of negative and positive charges. This recombination produces an emission of light with a color determined purely by the gas chemistry. In a laboratory environment, plasmas can be reproduced by flowing a gas into a vacuum chamber and igniting this gas with electric power. Depending on the type of gas flowing through the chamber, plasma can take on many rich colors. In the vacuum chamber, you can see argon gas emitting purple light. Nitrogen emits a reddish-orange light, and fluorocarbon emits blue. All of these different colors are specific to the gas chemistries. Plasmas can be used as a controllable reactive gas. So for example, if we put an object at the edge of a plasma, the charged particles will bombard the object, etching away at the surface. The electronics industry has used this concept to make smaller and smaller patterns into silicon, which is used in laptop computers, cell phones, and a whole wide variety of other applications. Plasma processing proved essential to the rapid miniaturization and increased performance of computers. These plasma processes are integral to the information revolution that is occurring today. Here at the University of Maryland, scientific research will continue to advance our understanding of plasma and its applications to make a better future.
All right. Pretty exciting stuff. Now, what is the most common state of matter in the universe? Plasma, made of highly charged particles. Describe the relationship between temperature and kinetic energy. As I said before, the more temperature matter contains, the more motion it will have, so the more kinetic energy. And if we have a lot of kinetic energy, those atoms and molecules are going to be further apart, therefore less dense in whatever container they are in, and vice versa. Then here I wanted to label the processes required to change water from one state to another by putting the correct word on each arrow or line. So if we go from a solid to a liquid, we are melting. If we go from a liquid to a gas, we are boiling or evaporation would be another way to say that. If we go from a gas to a liquid, we are condensing, condensation. And if we go from a liquid to a solid, we are freezing. And if we go from a solid directly to a gas, this is called sublimation. And that actually we have been seeing this winter. You'll notice there's a long period of time from when we get snow until we get the next one, but yet the snow level continues to drop. And a lot of times you'll see kind of a vapor haze across the countryside on a sunny day. Well, that's because the sunlight is making that solid snow crystal, it's giving it enough energy so that it immediately begins to vibrate with a lot of kinetic energy and goes straight from a solid to a gas. And so then again, you see that water vapor hanging around because of that. That's called sublimation. Sublimation. So what happens to cause the water droplets on the wings of the dragonfly? Well, the dragonfly does not generate its own heat. Therefore, the dragonfly is a little bit warmer than the surrounding area, but not by much, because it does have some metabolism and heartbeat and all that kind of thing going on. But on the wings are pretty cool. They don't, in terms of temperature. So water vapor that's in the atmosphere condenses into a liquid on the coolness of the wing. So the wing absorbs energy from the water vapor, making it condense or come closer together. It's not moving with so much kinetic energy to form the little droplets of dew on the wings. The law of conservation of mass or matter is the last thing we need to address. Mass or matter is neither created or destroyed, but is moved around. And the total amount of mass or matter moved remains the same before and after that movement. So just like any other law of conservation of something we've looked at this year, same thing for the law of conservation of mass or matter. It's not destroyed or created, but moved around, and the total amount is the same before and after that movement. The end.